MAI-Thinking-1 is a 35 billion active parameter mixture of experts model. It achieves frontier capabilities in STEM and coding, and it does so completely from scratch, without relying on synthetic data or imitating the outputs of other models. Out of the gate, it scores 52.8% on SWE Bench Pro and 97.0% on the AIM 2025 mathematics exam. This tracks the model's performance during reinforcement learning. We see 3 continuous upward trends across AIM, Live Code Bench, and SW Bench. Notice the x-axis. These climbs span thousands of training steps. This relies on one principle: capabilities must be natively learned. This contrasts with distillation, the common practice of training a new model to imitate the outputs of an existing, larger teacher model. Imitation allows a model to acquire basic abilities quickly, but as the model attempts to push past the limits of its teacher, its growth curve flattens, and its behavior becomes erratic. It lacks long-term steerability. Pushing a model through thousands of reinforcement learning steps without its performance degrading requires a rigorously optimized pre-training foundation. Microsoft AI addresses this with what they call the hill climbing machine. This is a system-level framework built on 3 pillars: measurement, architecture, and data. The framework strips the guesswork out of model design. Every pre-training decision is treated as a rigid mathematical optimization loop, driven by empirical testing. Enduring performance at the highest levels of reasoning requires an undistilled base model, tested and validated at every phase of construction. Before a massive model is trained, engineers must evaluate thousands of micro-decisions regarding layer counts and data mixes. Running full-scale tests for every variable would cost millions of dollars in compute. The standard approach relies on evaluating early models against generative benchmarks, like MMLU or math, but these introduce severe noise. These benchmarks require autoregressive generation. If the model makes a formatting error, like misplacing a LaTeX bracket, the error cascades, causing complete failure. To isolate actual intelligence, the team uses NLL evaluations. Here, the model is teacher-forced, predicting the next token against a known prefix. NLL tasks are computationally cheap to run, entirely immune to formatting noise, and provide a direct read on the model's predictive capabilities. This clear NLL signal enables the use of a scaling ladder. Engineers test architectural layouts at small parameter counts, knowing the efficiency data will accurately map to massive final runs. This schematic shows MAI Base 1's transformer architecture. The dotted line indicates a repeating sequence, interleaving high-sparity mixture of experts layers with zero-sparity dense networks. On the right, each token is compressed, routed to 8 of 512 experts, and expanded back. This specific layout was chosen using a metric called efficiency gain, or EG, which measures how much more compute a baseline model would need to match the performance of a new candidate. These scatter plots track efficiency gains. Engineers measured EG flops for theoretical efficiency and EG time for actual hardware wall clock efficiency. Looking at the horizontal dashed baselines, an alternative architecture using MOE in every layer yielded a higher theoretical efficiency gain in math, yet that design was rejected. When tested for actual execution speed, the MOE every layer design suffered from poor model flops utilization on the GPU cluster, dropping its time efficiency well below the required baseline. The interleaved approach provided the optimal balance between high theoretical model quality and physical execution speed. Architectural scaling requires hardware co-design, validated continuously by empirical efficiency metrics. The final pillar in constructing the base model is curating the 30 trillion token training mixture. Engineers compiling these datasets often rely on an assumption known as rank invariance. This is the hypothesis that if dataset A beats dataset B on a small 5 billion parameter model, it maintains that exact lead when scaled to a massive 35 billion parameter model. Experimental data gathered by the MAI team disproved this. At the 5 billion parameter scale, a data mix heavily weighted with STEM content outperformed a mix weighted with coding content on STEM evaluations. But when both mixes were scaled to 23 billion parameters, the performance curves crossed. The code-heavy mix overtook the STEM-heavy mix. The failure stemmed from a lack of diversity. 2 sources in the STEM mix contained high-quality data but significant internal duplication. The smaller model benefited from the density of those specific concepts. However, the massive 23 billion parameter model quickly exhausted all unique information within that dataset and plateaued completely. This flowchart details the HTML data pipeline built to prevent dataset saturation. The top row shows initial filtering, stripping boilerplate text, eliminating hash-level duplicates, and collapsing near-identical templates. Further down, semantic deduplication removes conceptually identical information, like standard algorithms written by hundreds of different programmers. To manage overlap across different data domains, the pipeline uses a global drop order hierarchy. This ensures that rare, high-value technical documents aren't erased if their text partially matches a massive low-value web crawl. Finally, mixing the data requires strict epoch capping based on the memorization risk of each specific source. For instance, highly diverse mathematical data was repeated over 5 times during the training run. Conversely, raw web PDFs contain repetitive structures and were capped at just half an epoch. At the frontier scale, high-quality data becomes a liability if it lacks the structural diversity required to feed hundreds of billions of parameters without inducing harmful memorization. Following the base pre-training, the model enters a mid-training phase. Even here, the team introduces no language model-generated synthetic data. Instead, they aggressively reweight the existing corpus, shifting the distribution to 55% code and 35% STEM data. These scatter plots track performance against a physics evaluation. In the web PDFs and web math panels, the downward slope shows that as these sources increase, error rates drop, improving reasoning. Conversely, the general web panel's flat trend contributes nothing to advanced reasoning. To refine the STEM data further, the engineers apply a filter based on the Bloom taxonomy of cognitive processing. This heuristic purges documents containing simple declarative facts. It retains only texts that demonstrate high technical correctness and complex analytical structure. This produces a dense, analytical, and highly steerable base model, which is finally handed over to the reinforcement learning phase. Returning to the reinforcement learning charts we saw earlier, the model executes steep, continuous climbs across both agentic and STEM domains. Sustaining thousands of uninterrupted learning steps is only mechanically possible because the underlying foundation was built on diverse, undistilled, and perfectly ablated data. MAI-Thinking-1 demonstrates that progress in frontier capabilities does not come from inheriting intelligence. It requires treating model development as a rigorous, empirical optimization loop from the very beginning.